In this video, we're going to cover angular momentum. As was done in the last chapter, we won't derive angular momentum from linear momentum. We're just going to substitute in the angular momentum values into the linear translational ones. So here's our equation for linear momentum. Remember again that this is a vector quantity. So its momentum is equal to mass times velocity. The angular momentum is also a vector quantity because it has magnitude and direction. Again, remember the direction is going to be either clockwise or counterclockwise. The angular momentum is equal to L, capital L, and it's equal to the moment of inertia, I, times omega, which is the angular speed. Remember, for all quantities in rotational mechanics, you need to make sure that your units are radians, not revolutions or degrees. The conservation of linear momentum states that in the absence of any external forces acting on the system, the momentum is conserved. This came from Newton's first law, and second law. And remember, I may have derived that for you in the 518 course. Okay, so momentum being mv, we can set this equal to, sorry, I'm writing with a mouse and my mouse stopped on me, m delta v over delta t. And what's delta v over delta t? A. Okay, so originally Newton had written his second law as the sum of the forces is equal to the change of momentum with respect to time. And actually he didn't write it as with the deltas, he actually wrote it as a derivative. So small changes of momentum with respect to time equal the net force acting on the system. So if there's no net force acting on the system, the sum of the forces goes to 0, and that means your change of momentum is 0. And that makes sense. If there's no change in momentum, that means there's no impulse, right? So no change in momentum means the momentum you start with has to be equal to the momentum you end with. Thus, there's no change in momentum. So Newton's second law, the rotational version, remember, is the torque is equal to I alpha, which is then equal to delta L over delta T. Okay? If there's no external forces, that means the angular momentum change must be 0. So there's no change in angular momentum when the net torque is 0. And when the net torque is 0, that also means the net force is 0. The standard example used to illustrate the conservation of angular momentum is usually the ice skater. You start by assuming a frictionless surface such as ice, and ice is pretty close to being a frictionless surface. It's not totally frictionless, but close. Okay? The skater starts with his or her arms out, and usually I see a girl skater versus a guy skater in the examples given, but we'll say either one. They start out with their hands stretched out, and they start spinning, and they go pretty slow, right? Then they pull their arms in, and what happens? They speed up, okay? So what happens to the rotational velocity after she or he pull their arms in? They go faster, right? Why do they go faster? Here's a video clip if you want to go ahead and copy or type this into your computer. Actually, what I'm going to do is I'm going to go ahead and copy and paste it. Actually, it won't let me do that. Okay, I don't know how to do that. But I'll just go ahead and, here we go, copy it. And then what I'll do is I'll paste that in my browser, and I will make sure that I have that available for you guys on Edmodo. Okay, so by assuming a nearly frictionless surface, that implies there's no net torque on the skater. So that means conservation of angular momentum can be used. Since the sum of the torque equals 0, the change in momentum equals 0, the momentum initial and the angular momentum final must be equal, and then we say that I omega equals I omega. Well, here's the thing. How does I change, right? How does that change? Well, remember that the human body is not a rigid sphere or a hoop or anything simple. But knowing what the definition of moment of inertia is, at what point is the spinning, in the spinning, does the skater have a greater moment of inertia? Is it when their hands are out or when their hands are in? Think about that. Write down an answer. Okay, let's see what we have. When the skater's arms are stretched out, more of his or her mass is located further from the axis of rotation, which happens to be the skates. So he or she has a greater moment of inertia when they tuck their hands or arms in. In the video, the initial moment of inertia is greater than the final moment of inertia. Thus, the final angular speed has to be greater than the initial angular speed, and the skater rotates faster when the arms are tucked in versus spread out. I need somebody to remind me tomorrow. I do have a rotating platform. We can hand you some weights and you can go ahead and check this out for yourself. So, a 2.0 kilograms solid spherical ball with a radius of 0.20 meters rolls with an angular velocity of 5 radians per second down a street. Magneto shrinks the radius of the ball down to 0.1 meters. I didn't know he had that power. But does not change the ball's mass and keeps it rolling. What is the new angular velocity of the ball? Okay, here are your choices: 10, 15, 20, 25 radians per second. Go ahead and pause the video now and solve the problem. I'm going to roll it up just in case you can't see the numbers. Okay, so let's see if you have the correct answer. The correct answer is C, 20 radians per second. Okay, remember that you're going to need to calculate the angular momentum, and because you're changing the radius, you're going to change the moment of inertia. Okay, from there you can find the new angular velocity, okay, since you have the same mass. So you're going to do angular momentum before equals angular momentum after and go from there. If you had trouble with this one, just go ahead and star it and ask me tomorrow in class. An ice skater extends her arms 0.5 meters out and begins to spin. When she brings her arms back to her chest, which statements are true in the scenario? There are two correct answers. She increases her angular velocity. She decreases her angular velocity. Her angular acceleration increases as she brings her arms in. Her angular acceleration decreases as she brings her arms in. Okay, so let's see if you selected the correct answer. Your answer should be A and C. She's going to increase her acceleration, and she's going to increase her angular velocity when she brings her arms in. Because remember, bringing her arms in decreases her moment of inertia. Since the angular momentum is conserved, it must be equal. Okay, and that is the end of the lecture, and that ends the unit. So get ready for that test. I want you to go ahead and start looking at the problems tomorrow night and the following night, and sometime this week we're going to finish up and have our test.